All right, chemists, let's get started. So if you aren't aware, I posted exam responses this morning. So the average for midterm 3 for this class was a 71%, which was right on target with what it was last year. So great on you for maintaining performance. So that was midterm 3. Remember, our final exam is cumulative and includes new content on chapters 12 and 13. So anticipate about a fourth of the final exam will be new material, and then the remainder of the exam will be review material. So let's just say every chapter will be represented equally for the most part. All right, that'll be for the final exam, and I anticipate to post some things, practice material, I don't know, sometime next week. All right, so there you go. With the exams, there was one issue with the grading of one of the problems, so I had to manually fix it for everybody. It's the cyclohexane question, so I manually fixed all the grades, and I put in the comment box what the actual right answer is, so your exam doesn't reflect the right answer, but I did fix it. So if you have any questions about the grading of that question, reach out to me. All right, so we are talking about big K, chemical equilibrium. We left off manipulating K, understanding, okay, big values of K. If K has a large magnitude, that tells us, oh, we have a lot of product present at equilibrium, versus if K is really small, there's a small amount of product, large amount of reactant at equilibrium, where K represents the ratio of concentrations of products over reactants at equilibrium. K also represents rate constant, but that relationship is not used as frequently. So we left off manipulating K and understanding how it works, converting between Kc and Kp, where Kc stands for concentration, Kp stands for pressure, so we can have different K values for aqueous things versus gaseous things. So now we'll go into the nitty-gritty of the math part, so this is the part you guys like, of how to use equilibrium constant. So up until now, we have been in equilibrium conditions already. I've given you equilibrium conditions, and we just plugged and chugged into the K expression and solved for the missing piece. But the idea here is, well, what if we aren't at equilibrium conditions? What if I give you a situation where you start with an X amount of stuff, some random amount of stuff, and you want to know what does your container look like once you've achieved equilibrium? That is what we're going to talk about now, where we start not at equilibrium conditions but end up at equilibrium conditions, and that requires using an ICE table. So in this chapter, we use ICE tables, which is very similar to BCA tables, but also very different. We set it up similarly, but we use it differently. So note that in this chapter, we're talking about chemical equilibrium. So we have the double arrow. We use ICE tables with chemical equilibrium because ICE stands for initial change equilibrium. But in chapter 3 and 4, when we did stoichiometry, we did BCA tables, which will, again, I'll show you what it looks like. It looks very similar, but very different in application. BCA tables, do you remember what that stands for? Before, change, and after. So in a BCA table, a full chemical reaction is happening. It's not an equilibrium. So typically there's like a limiting reactant. We're not using BCA tables here. It is very, very different, where the big idea in ICE tables is whatever concentrations you have in your equilibrium line, that is what goes into K. All right, so you start with initial conditions. The reaction has to change itself and follow stoichiometry. So this change line does follow stoichiometry, but this equilibrium line follows K, our equilibrium constant. Products over reactants, that number has to reflect the concentrations we actually measure. So that's the big takeaway from this section of the slides, is that this equilibrium line goes into K, whatever variables that may be. So let me show you an example of how we work an ICE table, right? So here's a random chemical reaction. Everything here, let's say, is aqueous. All right, so all of these things have a concentration. They're all aqueous. All right. So the power of an ice table tells us, allows us to calculate variables so we can understand more about the reaction that we're studying. So pretend I have a reaction, an equilibrium between A, B, there's no C, A, B, D, and E. Sure, okay. We start with 4 molarity of A and 3 molarity of B, right? That's what we start with initially. This reaction has to adjust itself to achieve equilibrium. This reaction is going to move itself so their equilibrium concentrations reflect the ratio that is dictated by K. So there's a strategy here. Look at what we start with. Can you predict which way this reaction has to go? It has to go which way? Forward. Yeah, towards the product side. How do you know that? We only start with reactants. There are no products. This reaction can only move forward. It cannot move backwards because we have 0 amounts of this. So this reaction has to move forward, all right? So that means I'm consuming reactants and making products. So that's where this change line comes into play. This change line is very similar to the change line in the BCA table, where the change line follows stoichiometry. So I like to think about it this way. Look at the stoichiometry for the reaction. For every 1A, you consume 2B, but you make 2D and you make 3E. So in our change line, I like to think of it this way. I'm going to lose an X amount of A. I'll pick a different color. Okay, I'm going to lose an X amount of A because the reaction's moving forward. But how much B do I also lose if I lose an X amount of A? 2X, yeah, so 2X. Cool. All right, what about D? It's also 2X, but be careful with the sign. Is it minus 2X? Am I losing 2X amount of D? Nope, I am gaining a 2X amount of D. And then finally, E, I'm gaining a 3X amount of E. So the change line reflects stoichiometry. That this reaction is just going to shift a little bit forward, or maybe a lot, I don't know, but whatever change happens has to reflect stoichiometry. All right? Okay, and so once we have I and C, initial and change set up, now we just add up our columns. At equilibrium, once this reaction achieves equilibrium, what we should see is a 4X amount of A 3 minus 2X amount of B, a 2X amount of D, and a 3X amount of E. All right, so the big takeaway from this slide and ice tables is that whatever is in your equilibrium line goes into your K expression. Excuse me. So we know already that K is products over reactants, concentrations at equilibrium. So simply the expression for Kc for this particular reaction is D concentration squared times E concentration cubed times, over A concentration over B concentration squared. See how I just did products over reactants? Stoichiometry or coefficients became superscripts, right? And so I said, ice tables. The E line goes into the K expression. So all of these values go into each of those concentrations. D concentration at equilibrium is 2X. That's the D concentration. This is the E concentration, but we need to make sure that we stay consistent with those exponents. So it's not just 2X, but it's 2X squared. So don't forget these exponents that are there. E concentration is 3X cubed. A concentration is 4 minus X, and then B concentration is 3 minus 2X squared. So there is a big, long expression. It has no solution because I didn't tell you what K is, but technically if I told you like K is 100, you could technically solve for X. Okay, not on a calculator, not you personally, but like you could give it to Wolfram Alpha and it could spit out what X is in this case and figure it out because there's just one variable. So that's the big idea here. The equilibrium concentrations go into that K expression. Again, this has no solution. I just want to show you how to set up an ice table with fake numbers. So the strategy for ice tables. First, you need that balanced equation. That's important for your change line. You need that K expression because the E line goes into K. And then finally, it's like playing Sudoku, all right? You have known values. Fill in your table. and then figure out, okay, what are the missing pieces and how can I figure out those missing pieces? All right, so let's do some ice table examples. There are two ways I can ask an ice table question. There's two types of ice table questions. And here's the first one. Because what you'll see here, and if you've ever taken chemistry before and learned about ice tables, you might associate ice tables with the quadratic formula, maybe. But the thing is you don't always need to use the quadratic formula for ice tables, and if you do when you don't have to, you're just being lazy. So let's look at this type of ice table and see if we can't just fill in what's known and figure out if we truly need to do a quadratic formula to solve for x. So here's the information. I call this question type 1. I give you initial concentrations, I give you a final concentration, and you calculate K. I call this, you Sudoku your ice table, meaning that you fill in the known values in your ice table, and that's enough information for you to fill in the rest of the ice table. So I'll show you what I mean. So a lot of this is just reading comprehension. We have a chemical equation, a chemical equilibrium. I know I'm going to have to do an ice table, but I need to just make sure I put those values in the right spot. So I tell you, we have a system containing hydrogen gas and iodine at this temperature, and we allow it to reach equilibrium. So to me, that sounds like initial conditions. These are like initial values. You start with that initially. So if we fill in this table, we start with 1 molarity of H2, and we start with 2 molarity of I2. So since I don't give you anything about HI, we assume that that's 0. And I tell you, at equilibrium, we measure an HI concentration of 1.82. So it looks like, okay, we have 1.87 molarity. Again, this is equilibrium. I tell you that this is at equilibrium. And I tell you, calculate Kc for this reaction. So Kc, just the generic expression for this specific reaction, is HI concentration squared, so products over reactants, H2, I2. Don't go trying to put 1 molarity and 2 molarity into this expression, because if you do, these are your initial concentrations. You want equilibrium concentrations in here. So to do that, we have to fill in the rest of this table and figure out what are these missing pieces. I tell you one of the pieces. What a lot of students will try to do is just do 1.87 squared over these two values, but again, only equilibrium concentrations go into this expression. So we need to figure out what are these missing pieces, and we do that by playing Sudoku, right? So remember how we set up this ice table. You know, we do our initial concentrations, we set up our change line, and we add up our columns. So if we think about this ice table, if we think about those initial conditions, which way does this reaction have to go? Forward again. So we can just make our x's in the change line a while. The change for hydrogen, for every x amount of hydrogen I lose, how much I2 do I lose? Minus x, but then how much HI do I gain? Plus 2x, yes. Do you see something that helps us determine x? Yeah, and what is that? We see that, oh, look, HI is changing by a 2x amount. So it looks like 1.87 molarity is equal to 2x. This allows me to solve for what x is. So x is equal to, what is it? Did I write it down? I don't know. Yeah, 0.935 molarity. Perfect. How does that help me? Because look, my goal is to get those equilibrium concentrations. So if I add up those columns, H2 at equilibrium is going to have 1 minus x amount of concentration. I2 is going to have a 2 minus x amount of concentration. I know what x is now. So I can just plug in that x into these expressions to figure out, okay, what are the concentrations of those two reactants at equilibrium? So we get that the concentration of H2, so you're just plugging in that 0.935 number in there. So the H2 concentration at equilibrium is something like 0.065 molarity, and then for I2, it is something at equilibrium is, so minus 2x. Or no, it's just minus x. So, what did I write? 1.065. So these are the two numbers that go into our KC expression. So I'll highlight those. We put this number in, everything that's in that E line. And then finally, this original number that was given in the actual question. This is the concentration of HI at equilibrium. Those are the values we put into the KC expression. It is equal to 1.87 molarity squared over H2. What did we say it was? 0.065 times 1.065. All right? And so then you get a number, is it like 51? Yes, it's like 51. All right, so I like to think of this as like playing Sudoku. You take the known values, you kind of half fill in your ICE table, how do things have to change? That allows you to solve for what X is, and then you can fill in the rest, get all those equilibrium concentrations, and plug it into K. All right, that's the first kind of ICE table. Okay, so how else can I ask these questions? So here, in this one, I gave you the I line. I gave you a hint at the E line. You filled in the rest so you can calculate K. So this question is the ICE table type 2, where you may or may not have to use the quadratic formula, which is why I have the quadratic formula in the corner there. This one's different. This one, I give you initial concentrations, but I give you K, and I want you to solve for equilibrium concentrations. So this one's different. It's like a different set of knowns, and the way we calculate it sometimes uses the quadratic, unfortunately. The ICE, my Sudoku method never needs the quadratic formula. If I give you initial and equilibrium concentrations, you have enough information to calculate K without the quadratic. But sometimes this one does. So I'll show you what I mean. All right, let's just approach this the exact same. Fill in what you know already. So we're going to do an ICE table for this reaction. And I tell you, here are your initial conditions. We have 0.1 molarity of AD and 0 of everything else. Which way does this reaction have to go? Forward. So what does my change line look like? Minus x, plus x, plus x. So at equilibrium, I have a 0.1 minus x amount of reactant, an x amount of A product, and an x amount of D product as well. All right, so what do we do with ICE tables? We take the E line and we shove it into K. That's what you do. But right now, everything in that E line is in terms of X. So let's write our K expression. K is equal to A concentration, D concentration, D concentration over my reactant AD concentration. I told you that this is 3 times 10 to the negative 10. It's a really tiny number, really small. So, like I said, the strategy with ICE tables is you always put the E line into the K expression. So I'm replacing all those concentrations with the actual expressions that I got from my ICE table. So K is actually equal to X times X over 0.1 minus X. And that is equal to 3 times 10 to the negative 10. You can go ahead and simplify that to x squared over 0.1 minus x equals 3 times 10 to the negative 10. Done. Boom. Okay. So you can, if you look at this expression, you can solve this. There's just one variable. You can solve it, but unfortunately, it requires the quadratic formula. If you move this term over here, you get x squared equals 3 times 10 to the negative 10 times 0.1 minus x. And if you distribute that coefficient, you get the quadratic formula, all right? So I don't know about you, but do you want to do the quadratic formula on the exam? Do you want to spend time doing that? So here's the quadratic formula. You put things in terms of a, like a x squared plus b x plus c equals 0. Do you want to do that? No, that takes a lot of time. I mean, you could do, if you have a graphing calculator, you can do it really quick, but here, let me show you a trick. We can use logic to simplify it, all right? The logic we can use, let me back it up here, all right? Back it up to the idea, let me just rewrite this, all right? It smells like burning bagels. X squared over 0.1 minus x, right? So this right here requires the quadratic formula. I'm lazy. I don't want to use the quadratic formula, so I'm going to use logic. K, is it a big number or a small number? Very small, very small. So that means what is mostly present at equilibrium in this reaction? Reactants or products? Reactants, if K is really small. So do we make a lot of products? No. So if you look back at this ice table, at first we start with a butt-ton of reactant. And you just told me you don't make a lot of product in this reaction because K is really small. So what do you think X is? Are you going to lose a lot of X or just a little bit of X? Just a tiny bit. So X is a really, really small number, very, very small, because K is small. So what is the consequence of that? Well, if X is really small, why don't we just ignore it on the denominator, right? Because if you have 0.1 minus a really tiny number, is the value of 0.1 going to change that much? It's not going to, all right? And so we can make an approximation here. Now it becomes a lot easier math, where you just multiply those two numbers, take the square root, no quadratic needed. So let me prove to you that you get the same answer within reasonable sig figs, all right? So again, the reason we can do this is because X is small. So this is the next slide. I will never force you to use the quadratic formula on an exam, but maybe on the homework, because you can just plug stuff into Wolfram Alpha, but never on the exam. You can always use an approximation that will get you the answer close enough to the right answer. So this requires the quadratic right there. That's what we just did, okay? Here are the two answers. Here are the two answers. If you put this into Wolfram Alpha, there's your answer, all right? So tell me which one, so you know you do the quadratic formula, you always get two answers. Which one is the answer we want to use? The positive one. We don't want to use that one. We can't have a negative concentration of something. So this is the number we want to use. That requires the quadratic formula. I don't want to do that. So remember the approximation that we're going to make. We're going to say this is really small. So we can ignore it. If it's so small, we're actually not going to really change the magnitude of the denominator at all. So we can simplify it to this. This is the approximation, where it's just x squared over that initial concentration equals k. And so simply, if we just multiply by 0.1 and take the square root, that's x. That's a lot simpler. You put this into Wolfram Alpha, look at those two answers. All right, and again, we don't want the negative value. We want the positive one. Tell me, do those two answers, with and without the approximation, do they differ at all? Barely. Do they differ within sig figs? No, they don't. Look, what sig fig do they actually start to differ? It takes the fifth sig fig. They finally start to differ, right? So to me, my eyes, those are the same answer. And so that's why this approximation works, where we can just ignore the minus x on the bottom if k is very, very small. Or sorry, if k is very, very small, we're not making a lot of product. All right? So again, we can always use the approximation in this class for exams. I'm never going to make you do the quadratic formula when you don't have to. All right, so let's do one more using a type 2 ice table where I give you initial concentrations, I give you K, I give you, I want you to calculate equilibrium concentration. So fill in the things you know. So here is your reaction. Let's fill in the ice table with the known values given. So I tell you here your initial conditions. Ooh, that sounds familiar. We start with half an atmosphere of AB. We start with, oh no, A2, that's not, where does that go? That goes there, right there, okay. Then we start with half an ATM of B2. And so I guess since they don't give A, B gas, that's 0. So this one's different. Which way does this reaction have to go? Forward or backwards? Backwards, yes, because there's this big void in reactants, got to fill that up. So the change line, so yes, this reaction's going backwards, but we don't need to flip the reaction. We can just say, oh, the reaction's going to go in reverse, so I can lose an X amount of A. I lose an X amount of B, but then how much AB do I gain? 2, so it's plus 2. So note that I don't have to reverse the reaction if I'm moving in reverse. I can just account for it in the change line. So you add up your ice table. At equilibrium, we're going to have a 2x amount of AB. We're going to have a 0.5 minus x of A2 and a 0.5 minus x of B2. What's the next step? E into K. Put the E line into the K expression. So I usually like to write the K expression. So K is still products over reactants as written. So we have A concentration, B concentration over AB concentration, but it's squared. And this is equal to 100 in the way it's written. So we put in those values that we, expressions we just got in the E line. So I get that K is equal to 0.5 minus X squared, because it's the same value twice for A square, or A sub 2, B sub 2. And then in the denominator, what is it? 2x, that whole thing squared, equals 100. All right. Can you solve that? Yeah, there's one variable. Should you distribute the square and then solve the quadratic? No, what's the trick you can do? Yeah, you take the square root of both sides. If you take the square root of both sides, this is a perfect square. So if you take the square root of that and take the square root of that, we can get rid of those two squares there and there in the numerator and denominator. So yeah, that's a perfect square. So then this simplifies into 0.5 minus x over 2x equals 10. That is not the quadratic. That is just simple algebra that you can now solve. That's a lot easier. So this one does not require the quadratic at all. I mean, though you could just plug it into Wolfram Alpha and get your answer, but there's a little trick here because it's a perfect square. And to prove to you I know how to do math, I'll solve it, I think. So I'll move that over there. So 0.5 minus x equals 20x. So 0.5 equals, 20x, equals 21x, so x is equal to something. I didn't write it down. Did I have it? Do I have it right there? Oh, I have it right there. Okay, 0.0238 atmospheres. Right? So I solved for x. Does that automatically mean I'm done? No, it doesn't. Look and see what the question's actually asking. I know you calculated something and you did it right, but if it's not what the question is asking, then you're going to be wrong anyway. So let's see, what are we trying to calculate? Oh, the equilibrium concentrations, the concentrations at equilibrium. So x is just a number. It doesn't necessarily represent equilibrium concentrations. What we do have at equilibrium is actually a 2x amount of AB. So what I'm going to do is actually shove this x back into the E line to actually get what are the actual concentrations at equilibrium. So AB concentration is not equal to x pressure, it's actually a 2x pressure. So it's equal to 0.047 atmospheres, so double that x value. And then these two values, A gas and B gas, they both have the same pressure. So I'm just being lazy here. So 0.5 minus x is something like 0.4476 atmospheres, right? So you actually have to plug that x back in so it has meaning to us. X doesn't necessarily always mean what our answer is. All right. So there we go. That's how we use our ice table. And to check your work, since we were given K, we can check our work and we can plug these actual values back into that K expression. So if we do that, if I do 0.476 squared over 0.047, you should get 100. I'm just going to assume you do get 100. If you put in those equilibrium concentrations we just calculated, that could help you double check yourself on an exam setting. Right, so here's another example of a type 2 question where I give you initial concentrations, but you can use a little trick to help you avoid the quadratic to get that to get x and then ultimately the equilibrium line. All right, so that's our ICE table, and we're going to be using ICE tables a little bit more in the following section. So here in slide 18, we talked about Le Chatelier's principle, but we already went over this on Tuesday, where, remember, whatever you do to a reaction, the reaction does the opposite to fulfill what you, or just to undo what you just did. So we did this on Tuesday, where we used Q. We used Q to predict which way a reaction can go. So we're going to move on to slide 31, where we left off. Right? And that is, we talked about K, equilibrium constant, we talked about ICE tables, we talked about Le Chatelier's principle, so now we're going to use different applications of equilibrium to discuss other phenomena in the world, and that includes solubility. So, the reason some things were really soluble in water and some things weren't is because of chemical equilibria. You remember this table? Remember using this table? Yeah? Did you ever wonder why? Why are these things soluble? Why are these things insoluble? Why when you put the soluble things in water they dissolve, and why the ones that are insoluble they don't dissolve? You never ask why? Did you care? Nah, no, not really. Maybe there's some part of you, some inquisitive part of you is like, well, why are hydroxides not soluble in water? Why are all nitrates very soluble in water? Well, it actually has to do with the phenomena of equilibrium constant, all right? So the reason that lead chloride, so if you look here, lead chloride, chlorides of lead are insoluble in water. The reason that lead chloride is insoluble in water is because this equilibrium expression right here, okay, lead chloride dissolving into lead 2+ and chloride minus, this has a very small K value. So if K is small, do you make a lot or a little bit of products? A little bit. So this reaction has a very, very small K value, so that means you don't make a lot of products within this chemical equilibrium, meaning you don't dissolve a lot of lead chloride when you try to dissolve it. So yeah, we see, the KSP, so this is K, it's still equilibrium constant, but it's for a specific type of reaction. We call it SP, which stands for solubility product, so dissolving salts in water. We see that lead chloride has a very, very small KSP, so it's not very soluble in water. Versus these substances that are very soluble in water, they have large KSPs, but these insoluble ones have very small KSPs, so you don't make a lot of products. So we'll explore kind of some of the consequences of these KSP expressions, right? And hopefully explain why some solutes are more soluble than others. Okay, so what is KSP? All right, it's SP, stands for solubility product. So we talked about KC. C stands for concentration. KP, P stands for pressure. SP stands for solubility product. So it means dissolving salts in water. So I have a salt here. It's barium sulfate. When barium sulfate dissolves in water, you get its ion. So if you think about, I guess, like your net ionic equation, remember we talked about like strong electrolytes and you split them up into their ions? That's essentially what's happening here. So you take that barium sulfate solid and you split it up into barium 2+ and sulfate 2-, aqueous. Both of those have concentrations. So KSP is the value that represents that chemical equilibrium. So we treat it like every other equilibrium we've talked about, in the past 2 days. Chemical equilibrium, the expression is just products over reactants. So the KSP for this reaction is equal to the concentration of barium 2+ times the concentration of sulfate. Do I put anything in my denominator? Do I put the solid in? No, solids don't have concentrations. Remember, K expressions, you do not put liquids in, and you don't put solids in. You only put gases and things that are aqueous, because those have concentrations. So we see here that the KSP expression, it's actually quite simple. We only have the products, and there's nothing in the denominator. So that's kind of nice, because then we don't have to like worry about quadratic stuff or anything. Okay, so KSP also helps us think about, you know, the extent of how much solids dissolve in water. So, you know, the idea that there's a certain point, a maximum amount of solid you can get to dissolve in water, and that has to do with KSP. Think about adding salt to water, right? You add a little bit of salt to water, that solid disappears, but really what is happening is that those ions are dissolving and becoming free in the solution. So all that solid dissolves. Well, what if you had a really big chunk of solid? Okay, well, some of it, more of it dissolves, but at a certain point, you add so much solid to your solution that no more of it will dissolve. At that point, we call that a saturated solution, where you have solid in equilibrium with the dissolved aqueous stuff around it. This is a saturated solution, and this is dictated by KSP. Whatever number that is KSP. If KSP is big, then you can basically dissolve a lot of salt before you reach a saturated solution, dynamic equilibrium. Or if KSP is really small, you can only add a little bit of salt before you reach dynamic equilibrium. So that's how it's related to solubility from chapter 3. Chapter 3, where we looked at commonly soluble versus insoluble salts. Really what they have are different KSPs in water. All right, so let's do the ice tables for these. What's nice is that they're easier because there's nothing in the denominator. So X, though, in a KSP expression, remember SP stands for solubility product, meaning we're dissolving salts in water. The X in a KSP expression represents molar solubility, meaning how much of that solid, how many moles of that solid will dissolve in 1 liter of solution. So that can tell us the extent of how soluble or how not very soluble a substance is. So let's look at this. Let's calculate the molar solubility of barium sulfate if the KSP is that. So I'm here to tell you that molar solubility, okay, this thing that we're trying to calculate, it's X. So really this question is asking you calculate X from the ice table. And we do this ice table the exact way we've done it before, but it's actually easier. So let's do our ice table. I tell you K for this reaction. So KSP, if you take you know, a look at this reaction, barium sulfate dissolving into ions, KSP is equal to just barium concentration times sulfate concentration, and that's it. No solid. So this one's tricky because I didn't tell you an initial amount. So this is what you're going to do for KSP expressions. Throw a chunk of the solid into the water. It doesn't matter how much. So I'm just going to say an N amount, N. So you might be thinking, well, why I have to choose a number, right? But here's the thing, does that solid end up in the KSP expression in the end anyway? It doesn't, so you can just put whatever frickin' number you want in there. I'm just gonna put N, I'm actually gonna put a letter, N. So if we start with an N amount of solid and 0 of the products, which way does this reaction have to go? Forward. So the change line looks like what? Minus X, plus X, plus X. So at equilibrium, I have an N minus X of barium sulfate. I have an X amount of barium 2+ and an X amount of sulfate. What's the trick with all ice tables? The E line goes into K. So when we put that into K, we get that the KSP expression reduces down into what? X squared. Anything else? No. So see how this N minus X didn't end up in the KSP expression, so that's why I can just put whatever frickin' number I want. I'm going to put N. And so what molar solubility represents is this X. How much I guess, solid do I lose when I dissolve this thing? And that is essentially what molar solubility is. Okay, so we got that KSP in terms of molar solubility as x squared. And so this is equal to 1.1 times 10 to the negative 10. And so simply we can just take the square root and get that x for this solution is what? 1.1 times 10 to the negative 5 molarity of barium sulfate, right? So what this means is that basically the maximum concentration you can get of a barium sulfate solution is times 10 to the negative 5 before the solid just sinks to the bottom. That's really dilute. Okay, I don't know about you. I have no idea how much stuff that is. I don't know. Is like 1.1 times 10 to the negative 5 a lot or a little? I mean, I know it's a little bit, but like I don't know how much. So it might be easier is to put it in terms of a different unit where we can convert that molar solubility instead to a gram amount per liter. That might be easier for us to visualize because I don't know what 1 times 10 to the negative 5 molarity means, right? But if I can convert this to a gram amount per liter, that might have more significance to me. So this is just, I guess, dimensional analysis. What does molarity mean? Big M, moles per liter. So we can rewrite this unit, x, molar solubility, as 1.1 times 10 to the negative 5 moles of barium sulfate is present in 1 liter of solution. So if I'm asking you, okay, how many grams of stuff can dissolve in 1 liter of solution? Let's start with 1 liter. Let's take that molar solubility we just got. I'm going to put 1 liter on the bottom, 1.1 times 10 to the negative 5 moles up top, moles of barium sulfate. So this will tell me how many moles of barium sulfate will dissolve. But I want this in a gram amount because I can wrap my head around grams, not so much moles. So for every 1 mole of barium sulfate, it weighs 233.38 grams. So what this means is in order to achieve that maximum solubility concentration, you need to put 2.4 times 10 to the negative 3 grams per every 1 liter. That is 0.0024 grams. So tell me, you've seen that number on the balances. Is that a lot or a little? That's a tiny bit. That's like nothing almost, right? That's like just having a speck on that balance. So that's only a tiny bit of barium sulfate can dissolve in a whole liter of water. That's a lot. You know, that's like just a little speck on that balance, right? So this number a lot easier to kind of visualize what that means, especially since you've had experience in lab using the analytical balances, which go out to 4 decimal places. So you know how sensitive those are. Okay, so let's do another one. So in this one, the KSP, I give you KSP, you tell me molar solubility. This is most similar to like a type 2 ice table where you're calculating X, essentially, molar solubility. But no quadratic needed because this is all, KSP expressions are a lot simpler. So let's do another one where it's just kind of flopped around. This time, I give you the molar solubility. I want you to give me KSP. So I'm telling you X, molar solubility, right here, 0.001713. I'm telling you the molar solubility. This is X in your ice table. And so I want you to tell me what is K. So our strategy is the same, it's just we're plugging in the numbers a little bit differently. So here we're doing not barium sulfate anymore. I'm telling you this is the molar solubility of lead iodide. So this is that really bright yellow stuff. Lead-based compounds are what are used on school buses. And you might think, well, why? Like lead is so poisonous, like that's a bad thing. But here's the thing, in terms of safety and chemical hygiene and chemical safety versus like children's being safe, yeah, a little bit of lead and its idea that it's not very soluble in water outweighs, you know, safety of children, or safety of children outweighs the toxicity of lead. That's what I'm trying to say. That lead-based compound's really, really bright, and you could never get that with non-lead-based paints. So when it comes to children, yes, lead-based paints are okay, but if you're just painting your bedroom yellow, I think you can get away with not using lead-based paints there. Okay, because safety isn't a concern. All right, so that was my spiel. All right, so let's go do the same thing. Write our ice table. Again, this is the KSP expression. So let's just take a moment and get that KSP expression. So KSP for this reaction, lead iodide dissolving, is the concentration of lead at equilibrium. But also the concentration of iodide. But what's different here? It's squared. Yes, it's squared. There's two of them. Perfect. Okay, now we do our ice table. Oh, but I didn't give you an initial concentration, so what should we do? Throw an N amount, just a random amount of solid in to get us started. So we see in order for this reaction to proceed, we have to lose an X amount of lead iodide, gain an X amount of lead 2+, but then how much I minus do I gain? 2X, yeah. So at equilibrium, I have an N minus X of lead iodide, and then I have an X amount of lead 2+, and a 2X amount of I minus. Remember, the E line always goes in the KSP expression, so KSP equals X times 2X squared. All right, here, I tell you, this is X. Here is your molar solubility of this compound. I am telling you how much the lead iodide dissolves in solution. So I'm telling you X. This X amount is 0.001713 molarity. So we see that this question is very similar. We set up the ice table very similarly, except this time we're using X to calculate molar solubility, or we're using X to calculate KSP instead of using KSP to calculate molar solubility. So you have to be cognizant enough that this is X. This is X. So we're going to stick that X into that KSP expression since we know what it is. Here's the KSP in terms of molar solubility, so it is equal to 4x cubed. So simply, it's 0.001713 cubed. And then we see, yeah, there's our KSP. It's a very, very tiny number times 10 to the negative 9. So you see, oh yeah, lead iodide, very insoluble. K is a very, very tiny number. So we see that not that much lead 2+ actually does dissolve in a liter of water, just a tiny, tiny, tiny bit. All right, and so children's safety is more important there. Or like the lines on the roads, right? Those ones that glow really bright, also made of lead-based paints, because being able to see the roads is more important than the tiny little bit of lead that is making its way to the waterways, right? And again, KSP is so small of it that water in contact with those road paints, very, very little of it is actually going into dissolving away. All right, so let's think about, all right, that's KSP, so an application of using ice tables. So let's do a demo. Yay. Okay, let's do a demo and disrupt KSP. Here's the thing. KSP, I wish we could spend more time on this part of the chapter because I think it's the most applicable chapter or applicable part of chemical equilibrium that you'll use today. All right, so I have pictures of Pinterest. You ever see these? All those crunchy Pinterest moms who clean everything with vinegar. Do you know what I'm talking about? Yeah. Okay. They're not totally wrong. They're not totally wrong. Have you ever looked at your shower head and see it? Oh, it's all crusty and stuff and scummy. If you ever Google how do I fix that? How do I clean it? Usually the first thing they'll say is, oh, soak it in vinegar. And there's a reason. And it actually has to do with KSP and disrupting chemical equilibria. All right. So let's use our ideas of Le Chatelier's principle and look at some cool things. So pretend pretend we have a saturated solution of sodium chloride. So right here, sodium chloride. See that? So it's a saturated solution. Pretend we add chloride. Add this. So add that. What does Le Chatelier's principle predict happens? Which way does the reaction go? Which way? Reverse, yes. So if the reaction goes in reverse, what should our eyeball see? Solid being formed. Yeah, all right? So let's see that happen. These goggles are very loose. Okay, so I have that right here. Right here I have a saturated solution of NaCl. Let's see if I can't, I don't know if this will work. Let's see, do the camera thing. Here, let me get my magic block of wood. Okay, you can see that? Yeah? Okay. All right, so this is a saturated solution of NaCl. So they made a saturated solution and then just filtered out all the solid, all right? So it is saturated, it has the maximum amount of solute dissolved, but what I'm gonna do is the exact thing that I just said before. Let me rewrite the reaction, all right? We have NaCl solid, the KSP expression is Na plus Cl minus. We're gonna add this, and so we should see the reaction shift backwards, and hopefully what we'll see is a solid form. So let's see. Let's see. So this is concentrated HCl. Oh, do you see it? So just a couple drops of HCl, and yeah, we absolutely see some solid being formed because we're pushing, using Le Chatelier's principle, and seeing it form more solid. So that's just a couple drops of HCl. So let me just add like a huge amount. Let's add a huge amount and see what happens. This is why I have to wear gloves. It's concentrated HCl. So add a bunch of HCl. What do you think will happen? Butt ton of solid. Oh my gosh, that's so smelly. I just want to make sure it's not ammonia. There we go. See? Yes, a lot of solid forms, and what we're really doing is disrupting, using Le Chatelier's principle to shift the reaction backwards. We see a lot of solid being formed. Okay, so that's kind of a cool demo to show. So what do crunchy moms have to do with this? So the other demo, so if you look lower on the slides, there's another demonstration that talks about, or another reaction that talks about the solubility of magnesium hydroxide. All right, so this KSP is magnesium hydroxide solid, dissolves into Mg2 plus and 2 hydroxides. Hydroxide is a base. Actually, let me just bring up the slides because I think that'll be easier. All right, come on. All right, yes, so there's that one. So magnesium hydroxide. This has another KSP associated with it, but we can do something different to a saturated solution of magnesium hydroxide. All right, so if we have like a very insoluble salt that contains a base, hydroxide's a base, right? What do bases do? How do they react? They will react with acids. So if I add an acid to this solution, adding H plus will react with hydroxide. So if I add H plus to react with hydroxide, what will I do to that hydroxide? In terms of Le Chatelier's principle, will I add more or remove it? You're going to actually remove hydroxide from this reaction because adding HCl converts it to water, something else. Now it's not part of the chemical equilibrium. So let me just reword that question. What happens when we remove hydroxide from this chemical equilibrium? Which way does the reaction shift, left or forward or backwards? Forward. If we remove a product, the reaction moves forward. So what should our eyeballs see? What happens to the solid? It disappears, all right? It disappears. So what we see is that a lot of solids, when they are under acidic conditions. When you dissolve some solids in acidic conditions, they become more soluble. And the reason is because they have a base present in the ions in the product side. Have you ever done the demo? Have you ever put an egg, like an egg in vinegar? Do you ever do that, like, experiment? You have? What happens to the egg when you soak it in vinegar for a long time? What? The shell disappears. Okay, the shell is made of calcium carbonate, right? So calcium carbonate is a base. So the acetic acid, the vinegar, reacts with the calcium carbonate, dissolving it away. And so that's how you're able to dissolve the eggshell away, but keeping that weird membrane intact. So that's exactly what you're seeing, that some solids become more soluble in acidic conditions. That's why a lot of toilet bowl cleaners are just strong acids. You look at the ingredients, and it's just a strong acid. All right, so let me show you this demo. Okay, so I have a solution of just magnesium right here. Oh, so let's do the picture thing. Let's hope this works. Boop. Okay, magic stick. Okay. Okay, you can see that? Yeah? Sure? All right. So I just have magnesium 2+ right now. That's the only thing. It's magnesium chloride. So that's the only thing you see right now. That's why it's a colorless solution. What if I add base to this reaction? Which way should the reaction shift? If I add, so right now I just have this and I add this. The reaction should move that way, right? So what should our eyeball see? We should see what? Do you see any solid right now? There is no solid. All it is magnesium. So if I add base, the reaction should go backwards. We should see solid being formed because now we have two products and it can go in the backwards direction, right? Because right now I have no reactant. So let me add base. Let's add base. Okay. Okay. All right, so what happened? Solid formed, right? How can you tell solid formed? It's now murky. Do we see it? Yeah, all right, so solid formed. So we can see, oh, if we start with this, add this, the reaction goes backwards, we make solid. Okay, so what would happen if I add acid? So if you think about Le Chatelier's principle, you might look at this and be like, oh, there is no acid. It's not going to affect anything, but acid is going to react with what part of this equilibria? The hydroxide. So adding acid is going to remove a product, so the reaction is going to shift which way? Forward. So what should our eyeballs see? The solid should go away. It should go away, yes, because the reaction is going to move forward. So let me add acid. Let's see what happens. Okay, let me give it a mix. Come on. Come on. There we go. See, the solid went away, all right? And that's because we added acid, it removed the hydroxide, turning it into water, and so Le Chatelier's principle predicts, hey, then it moves this, it goes back in the forward direction, so we consume that solid and it goes away. All right, so there's some demos. Okay, it went away. There we go. I'm gonna do some cool demos on Tuesday as well. We'll learn more about acids and bases, but I was gonna save those demos for next week. Okay, good? All right, so we got 20 minutes? All right, so let's keep going. Acids, bases. So we're going to talk about acids and bases a little bit more in terms of chemical equilibria. So this is, I told you that in 1220 we spend about 3-4 chapters on chemical equilibria. We're about halfway through what they've already learned in 1220. And so we're going to talk about chemical equilibria relating to acids and bases. I mentioned this earlier in the year, all right? We had, what, 7 strong acids to memorize, right? So there are 7 strong acids. We called them strong acids because they fully ionize in solution. Then every other acid in the world is a weak acid. There's only 7 you have to memorize that are strong. Let's remember, what are those 7 strong acids? HCl, HBr. There's a trend. Look at the periodic table. HI, yes. Anything else in that category? Strong? No. HF is not a strong acid. So there's 3. We're almost there. HNO3. So nitric acid is a strong acid. H2SO4 is a strong acid. And the 2 chloric acids, so HClO3, so chloric acid, and perchloric acid, HClO4, also a strong acid. So there's your 7. Those are the 7 strong acids, meaning if you put 1 molarity of HCl in solution, you will have 1 molarity of acid, H+. Versus weak acids, they follow chemical equilibrium. We mentioned this before, right? HF, you stick HF in water, only some of it ionizes. Ooh, do you see that double arrow? What does that double arrow mean? Equilibrium. So this HF also has a K associated with it, right? So we're going to talk about weak acids, how to calculate their pHs using their K values. But for acids, specifically, it's called a Ka. What do you think A stands for? Acid, yes. So it's a K specific for an acid. All right, and these are the equations you're going to use to calculate pH and pOH and all of that. So, all right. So let's talk about the pH and pOH scale. So I've kind of been lying to you a little bit. Pure water, H2O, is not H2O copy and pasted a billion times. I've been lying to you. Water actually self-ionizes, and there's a small amount of H+ and hydroxide present in all water samples. It's a very, very small amount, but we can quantify it using log scales, because I don't know about you, reading a bunch of zeros is annoying, so that's why they use log scales to signify how big or how small a number is. So these are those scales. pH is just a function. pH means take the negative log of H+ concentration. pOH is you take the negative log of OH concentration. What would the function P bananas mean? Negative log of banana concentration. Yeah, that's all it means. So, so to convert to these concentrations and to the pHs, you just take the negative logs of those. So if I start with a solution that's 1 × 10⁻⁵ molarity, H+, the pH is simply negative log that number, 1 × 10⁻⁵. So I want you to put this into your calculator and prove to you what these log scales signify. It's how many times you have to move the decimal place. So I already know that the pH of 1 × 10⁻⁵ is 5. Not because I'm smart, but it's because I understand what logs are. Once you do it a bunch of times with your calculator, you'll see that too, right? So let me point out the rule of sig figs. Okay, so when it comes to logarithms, the rule for sig figs is the number of decimal places in your concentration. The number of sig figs in your concentration is the number of decimal places in your pH. So if you look at H+ concentration, this number has 2 sig figs. So in our pH, 5 just means how many times I move the place value. So technically, that's not a measurement. That's actually an exact number. It's a counting number. So the rule is the number of sig figs in your concentration is the number of decimal places in your pH. All right, so the sig fig value actually comes after the decimal place. So truly, the pH for the solution isn't just 5. It's not just 5.0 to match 2 sig figs. No, it's 5.00, technically. All right, so that's the pH. Let's get the pOH too. So you might know that neutral substances have a pH of 7. And a common rule that we see is that if we compare the pH and pOH concentrations of a sample, they always add up to 14. But I'll Give you a caveat, this is only at 25 degrees Celsius, but 99% of the time we are working at 25 degrees Celsius. So if you know the pH, that means the pOH in this case would be 9, because 14 equals pH plus pOH. I know what pH is, so just go ahead and calculate that missing piece, pOH. All right, so let's work a little bit backwards here. So in this another example, I give you a pH of 11. So the H plus concentration, so to undo a pH, if you want the H plus concentration of something, it is equal to 10 to the negative pH. That's how you undo a logarithm. Or pOH, OH minus concentration is equal to 10 to the negative pOH. So that means H plus concentration for this solution is 1 times 10 to the negative 11. To get hydroxide concentration, you can kind of do a midway kind of analysis here. If pH equals 11, that means pOH is equal to 3, or 3.0, I guess. So that means hydroxide concentration is times 10 to the negative 3. Right? So there's something special about the relationship between these two numbers, and that has to do with the autoionization of water. If you multiply those two numbers together, the hydroxide and the hydronium ion concentration, you get that these two numbers multiplied together equal 1 times 10 to the negative 14. And that number is significant to us. And we'll talk about that on the next slide. All right? That's important to us. That's the relationship. That is why this 1 times 10 to the negative 14 is why pH plus pOH equals 14. Right? So there's a relationship there. So in terms of quantifying if something's acidic or basic, we actually want to look and compare at the relative amounts of H plus and OH minus present in a solution. H plus is acid, OH minus is base. So whichever one is bigger is whether the solution is acidic or basic. That is the true definition of acidity. So if we look in this first equation here, we see that the pH, where the H plus concentration is times 10 to the negative 5, the hydroxide concentration for this same solution would be 1 times 10 to the negative 9. So we see in this example, H plus is greater than OH minus, so this solution is acidic. Right? Or maybe you can think, oh, the pH is less than 7, so it's acidic. But that 7 rule, 7 being neutral, is only true for 25 degrees Celsius, and I'll show you an example in a minute. The second solution, pH 11, I have the two concentrations here for you. There's a tiny bit of H plus, times 10 to the negative 11. There are 11 or like 10 zeros. Versus hydroxide, only 2 zeros. So we see there's a lot more hydroxide present than H plus, so this is a basic solution. Very basic. So these are the rules. Your solution is neutral when H plus equals hydroxide, and that is pH 7 at 25 degrees Celsius. All right, so let's talk about the autoionization of water, why I've been lying to you all this time. You weren't ready for this, but now you're ready. Water actually self-ionizes. It's not a 100% pure substance where it's just like H2O copied a million times. Water actually ionizes with itself. And so how it does that is a water molecule will get close to another water molecule where one of the water molecules will steal a hydrogen from the other water molecule, leaving the lone pairs on that first water molecule. So what you see here is that two water molecules can become a hydroxide and a hydronium, basically a base and an acid, essentially. Right? This happens just a tiny, tiny, tiny bit. This autoionization, this chemical equilibrium, it's an equilibrium, look at that arrow, has a very small number. It's times 10 to the negative 14. Negative 14, that's a tiny number. So this doesn't happen that much, but it's enough to be significant, all right? And of course, this is at 25 degrees Celsius. We learned that K, the value of equilibrium constant, changes based upon temperature. So this KW value is only 1 times 10 to the negative 14 at 25 degrees Celsius. At all other temperatures, it's a different number. So I know what Kw is, the equilibrium constant for this reaction, so it might be useful for us to write out the equilibrium expression. It's products over reactants. But if you look closely here, only two of these things have concentrations. Water does not have a concentration. So if you look at the Kw expression, it's just the two products, all right, is equal to Kw, or K, just the normal K, or Kc for this reaction. But we call it Kw. W stands for what, you think? Water. Yeah, so it's just the Kc for the self-ionization of water. So chemists are lazy, though. We don't like to write H3O+. H3O+ means acid, it means H+, but it has an extra water molecule on there. H+ actually doesn't exist. It's always attached to a water molecule. But chemists are lazy and we don't want to write all those letters. So we oftentimes just rewrite it as Kw equals H+ times OH- equals 1 times 10 to the negative 14 because we're lazy. So technically pH is not correct. When you calculate pH, it actually should be pH3O+, but no one wants to say that. So we just say pH and understand that H+ actually is the exact same as H3O+. It's just missing a water molecule. But the assumption is that water is everywhere, all right? And so that H+ will always attach itself to a water, all right? Okay, so if this Kw is 1 times 10 to the negative 14, let's calculate the equilibrium concentrations and pH of pure water at 25 degrees Celsius. So we're going to do an ice table because water, the self-ionization of water, is a chemical equilibrium. So this is very similar to the KSPs we just did like 10 minutes ago. So right now we have a butt ton of water. We want to do an ice table because we want to calculate X in this case. So I'm going to throw in a random amount of water. I'm going to say N. Which way does this reaction have to go? Forward. So minus X, plus X, plus X. So at equilibrium, I have an, it's not minus X, it's actually minus 2X. But does it matter? No, because that ends up not being in the K expression anyway. So N minus 2X, X, X. With ice tables, the E line always goes into K. So if you write the K expression, in this case it's Kw, equals H3O+ concentration, or H+, whatever, times hydroxide, equals 1 times 10 to the negative 14. Perfect. So, just like with all ice tables, once you fill out your ice table and your change line, and get everything in terms of X and how it changes, we simplify it to, Kw equals X squared. That is equal to 1 times 10 to the negative 14. X then is, if you take the square root, is 1 times 10 to the negative 7 molarity. So that is the concentration of what? Look closely at your ice table. We calculated X, but X represents what? The concentration of H+, but also hydroxide. Yeah, so this X that we got does double duty. It is actually the concentration of H+ and the concentration of hydroxide. All right, and so since it's the same value, we see that, pH is equal to 7. POH is also equal to 7. So is this water neutral? It is, because H+ concentration equals OH- concentration. So let's just do one more. We'll do one more. Okay, let's calculate do the same thing. What is H+, what is OH of pure water, this time at 50 degrees Celsius? And I give you a different Kw value. It's the exact same. Let's do our ice table. We start with a random amount of water, minus 2X, plus X, plus X. At equilibrium, I have an X amount of acid and X amount of hydroxide. So we've actually set it up the exact same way. The only difference is when we plug this into the Kw expression, right? H3O plus times OH minus. x squared is now equal to a different number. It's not 1 times 10 to the negative 14. It's now 5.5 times 10 to the negative 14. But no matter, it's just a different number. We still take the square root of it, and we get that x is equal to something else. What is it? What is it? 2.345 times 10 to the negative 7 molarity. And so we see that x is, yes, equal to the H plus concentration. It's also equal to the hydroxide concentration. So if I go ahead and negative log that value, I get that the pH equals not 7, but instead 6.63. So based upon this answer, is water at 50 degrees acidic? Is this solution acidic? Is it acidic? It is not acidic, but it's less than 7. But what is the definition of acidic versus basic? Acidic means that the H plus concentration is more than the hydroxide concentration. But what's true about the concentration of those two things? They are actually equal to one another. So our definition that pH 7 is always neutral is incorrect. That is only true at 25 degrees Celsius. So this solution right now, this is actually neutral. All right, because pH equals 6.63. But you know what? POH is also equal to 6.63. All right, so this water with a different KW value is still neutral because H plus equals hydroxide concentration. And it's because the value of KW is changing. So water at 50 degrees is not acidic. Remember, the definition of neutral water is when hydroxide equals H plus concentration. So don't think that boiling water is acidic. It's still pure water. You didn't add anything to it. You didn't add any acid. The only thing that changed about it was the net amount of hydronium because the value of KW is changing. So we'll end with this. This is the last slide where I'm just going to relate all of those equations that we just did. So I mentioned we did pH at 50 degrees. We saw that, oh, you know, the pH of water at 50 degrees is like 6 point whatever. So at first glance, it might be like, oh, that's acidic water, but it's not. H plus is still equal to OH minus, so that water's neutral. 99% of the time in this class, we're going to work at 25 degrees Celsius. So the idea that pH, oh, my pen is dead. The idea that pH equals pH plus POH equals 14 is only true at 25 degrees Celsius. Because if you look back at this example, add up pH and POH, do those add up to 16? Sorry, 14? They don't. They add up to another number. They actually add up to pKW. If you take the negative log of this number, that's the value it adds up to. So putting it all together, I call this my magic square. It's magic because if you know any one of these corners of this square, you know all of it. Because everything is related to one another by either a logarithm or by KW. So remember, at 25 degrees Celsius, KW is 1 times 10 to the negative 14. So that's how these two values are related to one another. If you know the H plus concentration, you also know the hydroxide concentration because these two values multiply to KW. It's equal to 1 times 10 to the negative 14. You know those two, all right? There's always multiply up to times 10 to the 14. To go from H plus to pH, you take the negative log of H plus. To undo a pH, to go backwards, you do 10 to the negative pH. Same thing with OH minus. If you want to go to POH, you do negative log OH. But to undo a POH, you do 10 to the negative POH. Right? And then the last part of this magic square is relating pH and POH. These two values add up. POH add up to 14, but again, only at 25 degrees Celsius. And where that 14 comes from, 14 is actually equal to the negative log of KW at this temperature. If you take the negative log of 1 times 10 to the negative 14, you get 14. And that's where that 14 comes from. So why this magic square is magic is because if you know one part of this square, if you know this number, you actually know all three of them, all right? So they're all related by either KW or logarithms, and we'll be using them extensively, all right? So I believe the first 2 homework sets for this chapter is due on Monday. Yes, we passed that point. Yes. Yes. Parts 1 and 2 are due this Monday.